Okay, let's try for less phone ringing and more fun. We've got, as I said, electric flux. Okay. And for electric flux, what we're going to do is it's going to get harder and harder to keep track of that stuff. So in order to do it, let's say we have one of these sides. We know that one of these sides is going to have a bunch of area. Let's say length L. This is one side of our cube we had before. And if this is the area, we can actually define a vector that's perpendicular to that area. We're going to call it A. And A hat. So, not A hat, I'm sorry. Hat's the other thing. But it's a vector A. The vector A that describes the area from the side, this is, and again, the direction of the vector is out of the closed surface. So A is perpendicular, to the surface. Okay. But it's out of the closed surface. And that's going to define what we're looking at. There's lots of choices for a vector coming out of here, especially from a point charge. Let's say this is our point charge, and we're going to look at this as just a flat line. Well, some vectors are going to go like that. Some are going to go straight on. Some are going to go straight that way. And that makes sense. However, the only parts that are going to have the greatest effect are going to be the ones that come out of the surface. For us to keep track, we're going to have to find out what part of it is perpendicular to that. Or sorry, that's perpendicular to this side and parallel to this new A vector. Okay. So we're going to define something called electric flux. And that's going to be the dot product. So it's going to be a vector product of the electric field and the area vector for a closed surface. So the actual definition of it will be E dot A. If they're constant, that's pretty easy. It'll be E A cosine theta. And theta, remember, is going to be the angle between, if this is our A vector coming out of a side of a surface, and this is our E vector, our electric field vector, that's going to be theta. So it won't be measured from the surface itself, it'll be measured from a line perpendicular to that surface. And if E, the electric field, is parallel to A, then it will just be E times A. The flux will just be E times A, just EA, I guess. I don't need the dot, do I? And if you look at the units, they're kind of weird. They are newtons per coulomb times meters squared, which is Newton meters squared per coulomb. Which actually should look vaguely familiar to you. It looks a lot like the constant that we used, we attached to the K constant. So again, this is if they're constant. E for both of these, but this one's parallel. If it's not constant, then we have to add up, like I said up here, all these little bits. This part plus the next part, plus the next part, plus the next part, plus the next part, and so on. That sounds an awful lot like calculus, and it is. The flux is going to be E dot dA. Where we're adding up little bits of, we're adding up electric field along every little bit. If this is the side, we're going to break it into a bunch of pieces and a bunch of little vectors. So each one of these little pieces will have its own vector, and we will compare electric field to it along each little piece and add them together. And you can see that that is going to be some good fun. It's pretty tough when you have like one side of a thing, but it turns out not to be so bad later if you have a lot of sides. And some symmetry is going to be our biggest help in solving these kind of problems. So let's look at keeping a charge inside of a box. So it's inside the box. Now for this example, it's not going to be possible to do EA cosine theta because the field lines here and the field lines here and the field lines here won't be in the same direction. Since they're clearly not parallel, we're not going to use EA. The only way to solve this would be to do E dot dA. But there's actually a really cool symmetry that goes on with this. Let's say that instead, let's choose a different closed surface. Again, remember, we are choosing the closed surface. So it can be any shape we like of a sphere. So I've got plus inside of a sphere. I'm really bad with three-dimensional shapes. So we're going to have to pretend that's a sphere. And it has a radius of r and a charge of q. Well, we know the field from this for any charge is going to be kq over r squared. This is where we're going to start to not use k anymore. We're going to use 1 over 4 pi epsilon naught. It's going to be capital Q over r squared. Well, in this case, he's going to be constant across the sphere. Which makes sense. I mean, they're all the points on a sphere. It's a definition. It's all the points that are equidistant in space from one point, and that's the point where we place the point charge. So we can just, so for this one, we can just, and the other nice, so we can at least do EA cosine theta. Well, it's even cooler because every point is going to be exactly perpendicular to the surface. It's, again, assuming it's a sphere that goes around it. Because that's the case, we can get rid of this. So this is just going to be E times A. We got this half. We got the 1 4 pi epsilon naught Q over r squared, which is great. Well, but the surface area of a sphere, not the volume, is 4 pi r squared. One of the great things about the computer is I can't hear you all yell 4/3 pi r cubed, which is awesome, because then I just kind of look at you like, really, area? We don't need that. You can see cool thing happens. R squareds go away. 4 pi goes away. And we're left with Q over epsilon naught. So if we can find, the awesome thing about this is that it makes a link between electric field and electric force, a specific one. Which means if we take E dot dA for a closed surface, it will tell us the charge over that epsilon naught. In case you forgot, epsilon naught is the permittivity of free space. And it's a constant, always a favorite constant. It is 8.85 times 10 to the negative 12th Coulomb squared over Newton meter squared. We don't calculate very often with this constant. A lot of times in this section you're going to see we leave things in these terms. We're going to calculate for actual expressions instead of calculating for numbers, which I know drives some of you crazy, but that's the way it works. This thing has a name. It's called Gauss's law, and we will mess with that puppy about 1,000 times this unit. And I'm going to stop there. Have fun.